I hope you find solace in the fact that this is my last lecture over earthquakes before we move to tectonic plates. I also hope that you pondered the question that I posed in the last video, which is, can we predict earthquakes? And I'm going to take about a good 5 seconds to answer this. All right, can we predict earthquakes? No. Okay, I'm not going to bore you with the science of, well, scientist A said this and scientist B proposed this, because we don't actually definitively know how to predict an earthquake. Now, China had some really big strides in this area because obviously it's a heavily populated area. Earthquakes happen. They were able to predict one earthquake, but they failed in another. Honestly, my opinion on this is before we can actually set up an earthquake prediction center, that has to be so accurate, like 90 or above at least, because 90%. If you think about it, those heavily populated areas aren't just going to evacuate because you tell them there might be an earthquake. It's going to take a lot of time, energy, and especially money to move all those people out of an area like San Francisco. So in order to do that, you have to be really accurate. Also, another opinion of mine is that predicting earthquakes is about a few hundred years off. And the reason for this is we still haven't dug beyond the crust. Okay, I think the largest dig that we've done was I think it was the Kola borehole. Okay, I think that was around 12.26 kilometers. So we're still in crust territory. We haven't actually gotten a sample of the mantle or any of the cores, so we don't really know what's happening as far as earthquakes go. We've just been guessing. But I am going to spend the majority of this lecture on why we actually have all these layers and how we've been able to figure that out. So let's get going with that. Okay, so you'll recall back to chapter 1, the portion I had you read, that Earth can be separated based on a few different things. Okay, one set of layers that you can classify it based on is the chemical composition. Probably the simplest one to do, what are you made of? Okay, and that would include the crust, mantle, and the core, probably the ones you learned in 3rd grade or something. Okay, and the other one is going to be based on physical properties. And this one's a little more complicated. What is it doing? Okay, so this is where all the spheres come in: the lithosphere, asthenosphere, mesosphere, outer core, and inner core. And I want to make a little side note right here. Mesosphere, apparently that's not as popular as I'd like to believe, but I've seen it in a few textbooks. So I just want to specify right here that the mesosphere is actually the lower portion of the mantle. Make sure you know that. All right, so let's talk about this for just a brief moment. So the lithosphere is a very rigid rock. In fact, lithos actually means rock, so it's just a sphere of rock. Okay, and we're going to see in our tectonics unit that the lithosphere is broken up into discrete plates that move around and cause all these things like earthquakes and volcanoes to happen and all these plate boundaries. Okay, the asthenosphere lies right beneath the lithosphere, and it, as I like to call it, is liquid plastic, which means that it adjusts according to the weight from the lithosphere. So if you build a lot of mountains, okay, not you build, but if mountains accumulate in an area or glaciers deposit somewhere, all that weight is going to push down on the asthenosphere, and that's going to cause the asthenosphere to adjust. Okay, remember isostatic rebound and adjustment and equilibrium, all that fun stuff. So the asthenosphere is going to adjust. Right below that, we have the mesosphere, which is very rigid, and the outer inner core. Remember, the outer core is liquid, and the inner core is solid. You're going to have a composition of iron and nickel. Okay, mostly iron. All right, two factors play a role into these physical properties, so whether it's solid or liquid, and that is going to be temperature and pressure. If temperature were the only factor in this, you would have a crust that was solid and all the rest of it would be liquid, because temperature would increase and you just have liquid. But because as you increase, the pressure increases, which means it's really hard to break those chemical bonds and make it a liquid. So you remember that a solid is really packed, those atoms are tightly together. In a liquid, they're a little more spread out. So in order to get from here to here, all these bonds between the atoms have to break. And if you have pressure, they are all compacted in a solid. Okay, so that's why some portions, especially the inner core, is pure solid. How do we know that there are different layers? Well, there's a wave process called refraction, and I think in my optics playlist I'm going to make a few videos on refraction, but right now I'm just going to give you the basics. Refraction is the bending of waves when you transition from one medium to another. No, a medium is just a surface. or it's an area where waves travel. Okay, so like air, water, diamonds, wherever light waves or seismic waves go through. So the Earth is a medium. Seismic waves usually bend, and they're actually only straight when they approach a boundary head on. I'm going to show you this right now. So I'm going to use light waves as an example, and let's say that we have some sort of a boundary, and we're going to talk about two mediums or two areas. Okay, this surface, let it be air, and this surface, let it be water. Light waves are going to travel slower in water, but if you approach something head on, okay, a way to think of this is if this is perpendicular to the normal or the surface of reflection, this line right here, if this is perpendicular, then this light wave is just going to travel straight through, but it's going to travel at a slower rate. But if you have something where this is still air and this is still water, where the light wave is coming in at an angle, well, that wave is going to bend. It's actually going to bend kind of this way. It's kind of doing this thing. So throughout the crust and all the layers of the Earth, actually, we're going to see refraction happening all the time. Generally, especially considering that earthquakes originate and the focus is somewhere in the crust, generally speaking, seismic waves are going to travel faster as they descend through the Earth, especially the crust. And the two factors that are going to cause changes in wave velocity are density and elasticity. All right, seismic waves actually travel slower as you get more dense, so slower, and they travel faster as you get more flexible, so more room to move. But elasticity overcomes density, and elasticity actually increases faster than density as you go throughout the Earth, so that's why, in general, they travel faster. Okay, so here's the deal. Let's say that an earthquake originated from this point right here. Well, the way that seismic waves are going to bend through refraction is this. Okay, so this wave is going to come over here. And as you go deeper, it's going to be located at a distance a certain amount away. And you'd expect each of these to be kind of, kind of identical in distance. So this distance is equal to this distance because you're going down a constant amount. So they're proportional. That's the word I wanted to use. But eventually there's some sort of a boundary right here. There's some sort of a boundary. And if you go beyond that boundary, here's what's going to happen. So I'm going to do this in a different color. So this wave, start out in red, this wave is going to do the exact same thing. So it's going to come in, kind of refract a little bit. But then this portion of the wave through this different medium might actually travel something like this. Okay, so it's going to travel faster through this new medium, through this new layer of the Earth. Okay, see how it travels faster? Okay, and then it's going to refract just like regular. Okay, if you notice, these distances are fairly consistent, but this distance is a little shorter than all these other distances. So as we progress throughout the Earth, we're actually, especially through the mantle, these waves travel faster. So I hope that made sense. Okay, and this boundary through adjacent layers of the Earth is called a discontinuity. And the one discontinuity that I need you to be familiar with is the one that this Croatian scientist discovered, Andrija Mohorovičić. Okay, so this boundary, Mohorovičić discontinuity, or we're going to simplify it to the Moho. Just as a side note, I didn't know Croatian scientists were a thing. I'm like, oh, this guy was Croatian. That's kind of a big deal because you don't hear about Croatian scientists, but a lot of people were actually involved with this, like Nikola Tesla. I think he was born in Austria-Hungary, but some sort of an area that was Croatia. So here's the basic idea. Seismic waves exhibit very, very different properties in underlying parts of the Earth. Therefore, we know that there must be several layers with unique properties. I just kind of proved it for you right here. If waves travel faster a certain distance from the Earth's surface, then there has to be some sort of a different layer right here with different properties. And these different properties are what's responsible for this wave traveling faster through this medium. Okay, so there are two waves that I want to talk about the refractions of, S and P waves. So recall that S waves rely on shear stress to move waves that are perpendicular to the direction of travel. Okay, that basically means that if I have a solid right here, if I put stress right here, all these are linked by bonds. So if I put pressure on here, all these guys are going to move, and it's going to get shifted to the left. And then it's going to get shifted the other way. So that's kind of what's responsible for all this travel. So the direction of wave traveling in this direction, but it's actually kind of perpendicular. So it's going up and down. That's kind of what S waves are. But rigidity is a requirement, so it can only happen in solids. If there were liquids or gases, these bonds wouldn't be as strong. So if I put pressure on here, nothing really changes. And therefore, S waves can only move through solids. They can't move through liquids or gases. And because the only liquids in here, the only relevant one is the outer core. S waves cannot travel through this. Therefore, something called a shadow zone is created. And I want to show you that. So if I have a wave coming in directly to this boundary, perpendicular to this boundary, it's not able to travel through. There's just no way. I mean, it might the energy might try to go through here, but it just doesn't get transferred efficiently enough. But if I have a wave traveling at a slight angle, that's kind of refracted. It's going to move over here. This might move here, here. And these are all S waves, by the way. Okay, and at the very end, where it just almost touches the outer core, it is that. And this one, as it just touches the outer core, it might do something like that and refract. Well, all of this never sees any S waves travel. All of this. And we call that a shadow zone. So let me denote that. That's a shadow zone. Again, I want to say that it's about 130 degrees. Not for sure on that though, but it's definitely a lot more than you'd expect. P waves can go through all three states of matter, but they get refracted differently as they travel through the outer core and the inner core. So we have to kind of note that. They get refracted in the outer core. So I want to show you the other type of shadow zone that gets created. Okay, so if we're starting on and going head on, it's just going to travel through the outer core. It's going to travel through the inner core. It's going to go outward. But if you go at a slight angle, you might refract here, might refract here. And like with S waves, if I just barely take this surface, I'm not actually touching the outer core, it might get refracted to this point. If I go any more though, and I actually touch this outer core, what's going to happen is it's going to get refracted all the way over here because it's a different medium. And then from there, it gets refracted again because we switch mediums and we go out this end. So this area right here is another shadow zone. It's a P wave shadow zone. Right? So I'll do it with the other half just to be consistent. So let's say that I have a wave going here and just barely touching, but not actually going in the outer core. Well, if I go any closer, it's definitely going to hit the outer core, which means it gets refracted, and then it gets refracted again. And this is pretty messy, so I want to maybe do one where it goes through the inner core. I'll do it in black. So this one might get refracted, and it's going to get refracted again, and refracted outward, and refracted. So it keeps getting bent as you transition into different layers. So I want that to be kind of noteworthy to you. So shadow zones that get created are responsible, and this is how we kind of know that there are different layers. Okay, this shadow zone would only be created if this layer had different properties, and this layer had to be liquid, otherwise S-waves would be able to travel straight through it. So because there's another liquid layer of the Earth, we know that there's a shadow zone that's created. So the famous scientist that actually discovered that there's a separate boundary between the inner and outer core, and I know this is kind of random, her name was Inga Lehman. I don't see any situation where you'd ever have to know this, but I'm always pioneering for women in women scientists. She was a Danish seismologist, and she was responsible for the boundary, the Lehman discontinuity. She basically discovered that there's kind of a difference, and there's an outer and an inner core. So I just wanted to bring that up really quickly and randomly. All right, so that finishes our earthquake unit, and we're going to move on to tectonic plates next, and that's going to bring into account, well, earthquakes that happen at plate boundaries, but also the lithosphere, and how that's broken up into discrete plates that all move around. So I hope to see you in those videos.